Good morning. Good morning, everyone. It is really for me a pleasure to introduce you to Rohan Dahale. I have had the privilege, the fun, and the honor to be his supervisor during his stay here at the Instituto de Astrofísica de Andalucía. And today, so he is going to defend his PhD. Let me just say just a few words to introduce him. So Rohan joined the collaboration, the Event Horizon Telescope collaboration, in a really fascinating time. One of the most important times for the collaboration, and he has made very important contributions to the collaboration during his PhD. He first started working in the confirmation of the first ever image of the black hole that we obtained on M87. And after he worked on confirming this, the image of the black hole, then he led one of the most important papers of the collaboration, which was based on trying to get some extra physical understanding of the image, in particular whether we can constrain the metric around the black hole and to obtain a first determination of the spin. So he has led one of the most important papers of the collaboration in this regard. And after that, a really very exciting time for the collaboration. One of the most important goals of the collaboration now is to obtain the first movie of a black hole for the first time to understand how black hole accretion works. This is a turning point for the collaboration, and Rohan has made really instrumental contribution into that direction. So he has developed the framework of pipelines to test how robust our movies are going to be from black holes. So he has established the framework to determine the robustness of our future movies and to determine whether the data that we are obtaining with the collaboration is enough to get these reliable reconstructions of the accretion around supermassive black holes. After these 3 years working with us, I mean, I think it speaks, volumes about his leadership, his capacity, his really excellence as scientist. That he has finished his PhD in just 3 years. When he told me 1 year ago that he wanted to finish in 3 years, I told him, oh man. I mean, you will be my first student just finishing in 3 years. The common time is 4. And he has done that and more. And today we also are honored to have here Adia Levis from Toronto University. He is the chair of the panel of the committee of Rohan's defense, and he will move to do his postdoc at Toronto University with Adia. So with that, I leave you, Rohan, to tell the full story with all details, and I pass it to the panel. Thank you.
Just a couple of logistical things. So before we hear the exciting work of Ron, I'm just going to introduce myself and the committee. So we have here Uta Lisenfeld, who's going to be the secretary of the committee, and she's a professor at the University of Granada. We have Maciej Wilgus with us from the Institute, which you guys probably know, and he's going to be a committee member, and then I will chair the committee. And Rohan, you have about 40 to 60 minutes to tell us all about your exciting work, and then we're going to proceed with some questions, and we'll take it from there.
Thanks, Jose, for that nice introduction. So
switch to some so you get like press buttons until you're happy.
yeah, sorry. So hi everyone. I'm going to talk all about what I've worked in the last 3 years. As you can see, the title is Inferring Black Hole Physics Through Images and Video Reconstructions with the Event Horizon Telescope. And I'm going to decipher what it means and what I've done throughout this talk. But before that, I want to mention that I did this PhD as a Lacaisha doctoral fellow through the Lacaisha Foundation's fellowship. I want to acknowledge their support for this. Other than that, I also want to acknowledge the great things that I've learned from Jose throughout the 3 years, and also the whole group. Thank you very much for that. And so I'm going to defend this thesis. It's a part of this doctoral program in physics and space sciences. So yeah, that's about it. And let's begin of what there really is behind this title. So the first natural question when I mentioned we are going to look at images, why should we even image black holes? I mean, people ask this all the time. What is so secret in EHT and why do we make images? I think one of the most easy answer is that black holes are a direct consequence of the Einstein's general theory of relativity. And imaging them allows us to test GR in the strong field regime. That's one of it. Other than that, we can also observe the black hole shadow, which is one of the key predictions of GR. And then also we can also study black hole accretion and also jet launching by making images of black holes. Not just images, but now we're also getting into videos. So these would be the main reasons why we would want to image them. But what has been in the past in this regard? So EHT has already published amazing with these images of M87 star and Sagittarius A star, which are at the center of the M87 galaxy and the galactic center. And the great thing about this first direct images is that they are the largest black holes in the sky, but they have mass that is almost 1,000 of order difference. So over 3 orders of magnitude of different masses, and we could still test GR in the same way. And so we have had this great images. We did a lot of science with it, but there are still some outstanding questions. And we are going to look at these outstanding questions and how I use these questions throughout my thesis to answer them in different chapters of this presentation and also the thesis. So firstly, the natural question is, we saw the image of M87. The question is this shadow persistent over a yearly scale? And how does it evolve over a yearly scale? So how does the emission change in M87? So we're going to look at that. And then that we have actually measured the mass of black hole through the size of the shadow, but we still don't have a measurement of spin. And that's one of the other important parameter when we look, we want to fully describe the space-time metric. So we will try to see if we can attempt at measuring spin and what directions we can take towards measuring spin. The third thing is, since I mentioned videos, we also want to answer the question like, how exactly is matter accreting around supermassive black holes? So these are the 3 questions that we would try to answer through 3 chapters that we would go throughout this presentation. And that would be done by, firstly, we would look at the 2018 data of EHT for M87, and we would make images and see how it looks. So that would be one part of it. And we would use different methods, a different newer method to do so. And then for the question of measurement of spin or how matter accretes, there are 2 more chapters. So the first one is we will look at the image of M87. You already saw once, and the question is whether it's circular, perfectly circular or not. And if it's not circular, then why exactly isn't? Is it really due to the gravitational effect, or is it's an astrophysical effect? The third thing that we would look at is the next big thing is really just making videos, the next frontier of black hole physics. So through that, our attempt is to understand black hole accretion, maybe to also try to attempt measuring spin. I wouldn't be talking physics of it, but I would be mostly talking about, can we trust these videos when the data is so sparse? So I'm going to describe how I'm going to structure this talk. Firstly, we will go through some methodological things, how to do imaging and how to extract features in order to do any physics out of it. And then we would go through these 3 chapters that I just mentioned, which are part of 3 different papers. And at the end, I would describe all the conclusions and how we can go forward from there. So I would start with the story of what is Event Horizon Telescope. And it's essentially just a very big telescope that's almost as big as Earth. But we cannot put a telescope that's as big as Earth. It's just a virtual telescope. So in reality, what we do is we put different antennas throughout the globe, and they're computationally linked. And this computational link acts as a huge Earth-sized virtual telescope. And so the lines connecting here on the screen actually show the thing called baselines. So they're computationally linked. And so we measure the data through different orientations of these telescopes. And these different orientations give us information about different parts of the source in different directions. And when the baseline is longer, then we measure the finer details. And when it's shorter, we measure the more extended features. And so through this procedure, we try to measure, try to get an image. But how exactly is done in reality is that the Earth is rotating, and as Earth is rotating, it's actually sampling something called spatial frequencies, which we call UV coverage, and you can actually see how the image gets improved when we have more and more coverage. So this is not as straightforward as it is in things like optical imaging, where you would just take an image and direct Fourier transformation gives you an image. We really have very sparse data, and so we need like special imaging algorithms to deal with this sparse data. And so I would be talking about some of the data terms before we go on to how to image this. So we actually took the data. So let's look at how exactly the data looks like. So what we measure is visibilities. So visibilities are when we correlate signal from these two interferometer setup that I'm talking about, and we have many of these two interferometer setups that we are measuring. And what we measure is the amplitude of how strong the signal is in one location, and that where it is strong is given by the phase part of it, and that's called one visibility when we measure at one correlation from at a time. And when we put this together in the context of polarization, full polarization, then we also have the left-handed and the right-handed circular polarization, and the matrix of them together correlated, all permutation combinations of them forms the coherency matrix. And then from this coherency matrix, you can form our usual Stokes IQU parameters. And so this is what ideally a source would look like. But then we also have things like the telescope terms. Sorry. So we also have things like the calibration terms that the telescope goes through. So there is atmosphere, and there is also the instrumental terms that corrupt our signal. And that is encoded in this so-called Jones matrices. And you can see on the left, this one is GR and GL, which are the gains on the right and left hand circular polarization. And the other matrix is for the leakage, which corrupts the crosshands. And so when we get the signal, we actually get this matrices multiplied to our source signal. But when we want to image things, we want to be immune to this calibration terms from the telescope or from the atmosphere. So we already do some calibration while we correlate the data, and after that. But then in order to do imaging, we have certain quantities that are immune to this station-dependent phase errors and also amplitude errors. So they are just a 3-pair telescope. You take the phase of it and add, and when you add some error to each quantities, it cancels out. The other is the amplitude, where you just take a pair of 4 telescope, and then from this quantity, it gets insensitive to amplitude gains. So these two quantities are very useful when we do imaging, and you will see further more about gains and also these quantities when I describe imaging. So I'm going to only talk about the only imaging algorithm that I've used throughout this work, which is the COMRAD algorithm, which is a Bayesian imaging algorithm. And there are several other algorithms used by the PhD in different papers. I'm going to describe only the Bayesian one, which is what I've contributed the most. So why Bayesian imaging? Because we already saw that the UV coverage is very sparse. So there is this inverse problem is inherently ill-posed, and there is uncertainty in it. So there is inherent uncertainty, and so we need a method that can quantify this uncertainty. And Bayesian imaging can do this naturally by defining a thing called posterior. So because we have observed data, and then we want to measure what is the probability of an image given a data that we have observed. So for that, what we do is we define a thing called likelihood, which essentially measures for a potential image how well it matches our measurements. And to do so, we have to also need a prior knowledge. And this prior is basically what is more of a plausible image. And it encodes things like it should be smooth and not just random noise. There should be spatial correlations. So instead of describing a best image in Bayesian imaging, we actually define a probability of images. And actually, since we have model parameters also for the telescope calibration terms, we can also get like the probability distribution of these terms and quantify uncertainties for that. So for COMRAD imaging, for the work that I've used in this thesis, we initially just use an independent pixel grid prior, which is each pixel is actually a different model parameter, and there is no correlation between the pixels. Later on, we also developed more priors that introduce the spatial correlations. We used actually visibility amplitude and closure phases. Since the atmosphere corrupts the visibilities, we actually use closure phases, which are independent of this station-dependent phase errors. So, and on top of it, since we are fitting visibility amplitudes, we also need to think about the gains in amplitude. Now, since in Comrade we can fit for these gains and get the probability distribution of them, we actually fit for these gain amplitudes as well and get the probability distribution. Once we have defined this posterior, we can then sample the posterior. For that, we use this technique called Hamiltonian Monte Carlo sampling, which is essentially an MCMC sampling, but we also used the height of the posterior to sample it well. If it's bimodal, it's easier to jump from one location to another by measuring how high things are, to sample more where we have more probability. And so the great thing is we did not have, the good thing is we did not have this posterior of telescope terms before, but now with Comrade, we could also have that. So now that we have described imaging, I want to also describe another tool, which is once we have images, how do we even extract features from it so that we can do any physics with it. So one of the feature extraction method is called ring extractor, which is part of an imaging library already called EHT imaging. And this, what we do is we slice it along radially. And for each radial slice, we measure the peak intensity. And we sample this throughout the all 360-degree angles. And then we calculate the mean and the standard deviation of that distribution to calculate the mean and the standard deviation of the radius. So that's one way of to do it. And the another software to do this is called variational image domain analysis. This one is in Julia. The previous one was in Python. So here the approach is a bit different. What we do is we define a template. So essentially some geometric template that has parameters like the ring size, the width, and where is the position angle, and all of that. And what we do is we optimize the parameters of this template until it best matches the image in the image domain. And the way the optimization is done by defining some divergence. In this case, I have defined a divergence based on a cross correlation between the template that we have versus the image, and we minimize this divergence until we have the best fit. And here, what I'm showing here is the cross section in horizontal and vertical lines for both the image and the template. And you can see it quite matches well in both colors. So this is one of the technique for the images, but then next we will talk about another technique, which is for videos. So now that we're entering this new era of videos, we also need to have new methods that can extract features from videos. So the way we do that is, I have already described Rex, which is the ring extractor. And we extract the ring radius and the error to that radius for each timestamps. For each frame, we extract these slices. And those slices, we look at the intensities and we plot it here. So each time is one slice and then another slice. So we do it for all slices. And then on this slice, on this plot, we perform autocorrelation. So the autocorrelation plot would tell us if we use this autocorrelation plot and compute the second moment, you would get like a mean pattern speed. So meaning how fast the features are moving on an average on this ring that we have selected. So this would be quite useful when we look at all the methods to validate our video reconstructions. So now that we have all the tools briefly described, we know how to take data, we know how to image them, then we can also use different tools to extract features from both images and videos. We can now jump straight into actually imaging them and then looking at some of the results that I described before. So I'm going to talk about, firstly, about imaging the 2018 M87 data with the EHT. And I will try to answer this question, that the shadow that was seen in 2017, is it still the same year later, and has anything changed? And we will try to look at what has changed and why. And this paper was actually a part of the Event Horizon Telescope Collaborations paper. My contribution was mostly to the imaging part using Comrade. Just to note that this is actually a big collaboration effort that was done. So firstly, what has changed? We have already seen the 2017 images. But what has changed the new data? Firstly, we have this new telescope GLT that is on the north that has this coverage. You can see the baselines that are in orange that cover north and south directions. And that gives us additional coverage, giving more constraints in that direction. So that's one. We observed actually many different days, but one of the best days that has the best coverage, more point sample, is the April 21 in 2018. So other than adding a telescope, we also doubled the bandwidth. Previously, we were using just at 200, about 217 gigahertz, and we doubled that to also 227 as well, and 2 bands there. Other than doubling the bandwidth, we actually increased the sensitivity of one of the telescope in Mexico called LMT, the Large Millimeter Telescope. And so these 3 things definitely improved our data quality. But then what exactly changed in the source is still a question. So firstly, before even we imaged M87, we usually, as we do in EHT, we did a lot of tests to validate both our data and our methods so that we can trust the actual images of M87. So for that, what we did is we actually designed a lot of geometrical models, the crescent, a ring, a double, and all of them, you can see they match the visibilities of M87 fairly well. So actually anything can describe M87. So we need to be very certain of what we are looking at. But as you can see, most of these methods, they get very good reconstructions and they can recover the truth quite well. But the way this was done actually was making a lot of images through many different algorithms. As you can see, there is DiffMap, which is a clean-based approach, which is the traditional way of doing it. There's EHTM and Smiley, which are regularized maximum likelihood methods. And there is Themis and Comrade, both Bayesian imaging methods. So we actually made, I counted almost 1 million order of images, both by sampling the posterior and also like all other imaging methods, made almost 1 million of images. And how did that happen is we took the 4 of these models, and for methods like DiffMap, EHTM, and Smiley, we imaged and correlated them with the ground truth to figure out the best parameters that it gets. And on those parameters, we validated them applying these parameters to the rest of the models and see how good they are. So they were validated with the green models marked in green. And then for the other methods like Themis and Comrade, we don't really need any such selection of parameters called topset. All the models are for validation. So after we have validated these images, we made the image of M87. And as you can see, the big difference from 2017 to 2018 is that the position angle from the south has changed a bit towards counterclockwise by 30 degrees. That's one change. But one thing that is easily observable here is that the ring size is almost the same. We would extract the ring size later on and see how well it is agreeing with 2017. So these 2 features are outrightly visible, but we would actually quantify them later. So firstly, is this consistent among all the methods? Yes, we actually checked with all different methods. And then since they have different resolutions among themselves, we match the resolution. And then after matching the resolution, they look quite similar. On top of imaging, we also had a geometrical modeling, where a priori we assume different set of models like a ring model or a disk model, and all those models actually converge on giving us most likelihood as the ring type of models. And for all those ring type of models as well, we have the or for all the geometry. Sorry. Yeah, for all the modeling as well, we get the same image as we got in imaging. So this is actually quite consistent with each other and a relief. So after looking at all the different kinds of imaging, I would also specifically point out at Comrade imaging of this data. Because previously what we showed was just one image, which is a maximum of posterior image before sampling the posterior. Here I'm showing the posterior where there is the mean image, the standard deviation of the images that after sampling. And then most important one is actually the fractional standard deviation, where we are dividing the standard deviation by the mean. And from here, we can see that wherever there is a ring emission, it's quite low fractional standard deviation, meaning that the ring is very, very certain, and anything outside is not that certain. So so the ring is actually quite confirmed and has high SNR in that region. So after we have actually looked at different images, the natural question is, okay, the ring size looks similar, but is it really that similar? How similar it is? So for that, we used the previous tools that we described, Rex and Vida, and then we measured the ring diameter and also the position angle. And from that, we found out that the 2017, obviously the published results had 43, and then within the error bars, the 2018 is still consistent. So we actually expected exactly this because M87 is accreting very slowly. So with this accretion, we actually expect the mass of the M87 to be fairly constant over 1 year. And for that, we expect the same ring size. So that's one confirmation that GR is still correct. But the other one we still need to understand, which is why did it went under a counterclockwise shift by 30 degrees. So for that, firstly, we will look at what it means by getting a diameter of 42 or 43 that we saw within the error bars. And there is a quantity called the gravitational radius that is independent of the model or the imaging methods we use. So since we have very different kinds of theoretical models and also the imaging methods, we actually need a common quantity that we can compare 1-to-1. And that quantity is defined by this ratio of the mass and the distance from us and other constant parameters in it. And so to get this, since the models are actually are dependent on what kind of physical parameters we use, the spin, the different kinds of accretion rates, and so we can convert this through by finding out what is the scaling factor between the radius that we find versus this common gravitational radius. And in 2017, we found this as 10 to 11, and there's about 10% uncertainty in this. It was very well calibrated in that. In the 2018 paper, we actually did not calibrate this again. We just used this scaling factor again to calculate this gravitational radius. And that's what I'm showing on the right here. The gravitational radius is shown in the y-axis, and all the different imaging methods are shown on the x-axis. And so the different feature extraction methods are also shown in different colors. And you can see that the 2017 ones that are in the boxes are actually within the error bars quite consistent with the 2018. So now we can measure the mass of M87 after 1 year, and it's still the same. So next we will look at the other feature that we had measured, which was why is there a shift in the position angle? And the answer is actually quite straightforward. So if you just focus on this simulation, general relativistic magnetohydrodynamics simulation, you can see that when it's blurred, the position angle actually changes over the scale of weeks to a year. And what we actually had in 2017 was just one snapshot, and then 2018 was another snapshot. So this is just a direct view that the matter is turbulent, and we're just taking different snapshot of this different turbulent matter. And so the next thing that we can see from the position angle is actually just by looking at where the position angle is, we can figure out which way the black hole is spinning. So it's still in the same direction, it's downwards. So meaning the spin is still away from us. And this was also strongly favored in other previous papers. So that's still consistent with what we had previously. And then the second thing is from the position angle, we can also look at the large scale jet, or what direction the large scale jet is. And it's consistent with the large scale jet as well. So in all, the results are consistent. We know the ring size is same, and then we also know why exactly the position angle shifted and what it really means. So now that we have actually looked at the images of M87 in 2018, the next natural question is, okay, the ring looks not exactly circular. It looks a bit elliptical. And we will now ask this question, why exactly it's not circular? It could be a gravitational effect because it's spinning. It could also be an astrophysical effect. And this paper is actually an official paper of the realistic collaboration, which I led with Ilje, who was another colleague of mine. And so this was a huge effort as well. And I just wanted to highlight that this is also another PhD paper. So, okay. Firstly, we will try to understand what exactly it means by gravitational effect or astrophysical effect. And for that, we would look at this very nice movie that shows that whenever the photons are actually just going around the black hole without turning around it, that's a direct image that we see. But then when we look at the photons that orbit the black hole and then come towards us. That gives us a sharper signal of the gravitational effect. So actually, if we look at what the orbiting light, that is what we actually would need to see the spin effect or the gravitational effect. So in order to test GR, we would need to find some signature of this orbiting light. And so first I'm going to describe what it means by gravitational effect and why it changes the shape of the shadow itself. And that happens because when the black hole actually spins, and given the inclination of M87 with its uncertainty, even if it's like 27 instead of 17, with that we see actually that the ellipticity of the shadow goes only up to like 4%. And that happens because the black hole is spinning and the space-time itself changes. So that actually makes the ring more elliptical. So this could be one of the origins that could make the ring elliptical, but there could be another source of ellipticity that could make the ring elliptical, which is the emission and the accretion flow itself. So we have some truth. We have seen some simulations. If we do a finite resolution of it and do make reconstructions, we could have this ellipticity coming from this accretion flow as well. And we can label this as emission ellipticity. Other than that, since we have very sparse coverage and the data is corrupted and we have different algorithms, these can create a bias in what we are seeing. So we have to actually first get rid of this bias and figure out if we have a bias, even before answering the distinction between emission ellipticity and gravitational ellipticity. So in order to do so, firstly, we will look at what changed in the 2018 data. We saw this previously, but we'll look at in more detail, which is this coverage from GLT is the Greenland telescope is marked in orange. And you can see the north-south, as I had mentioned before, has filled up. So the data is better for one. So maybe this helps now. And the second thing is, with this improved data, the question is it enough to recover the ellipticity for synthetic data tests? So to do so, what we did is we performed a Fisher information analysis, which is essentially that assuming a given model, around that model, we calculate a posterior. And for that, we calculate what's the width of that posterior for a particular parameter. We're only looking at the ellipticity of the crescent model and what angle it's oriented. Around that, we calculate how wide it is. So it essentially encodes how much information we have about that parameter in that data. And what I'm plotting here is the value of this width for all sorts of different values of elliptical crescents, of different ellipticities. And then along the y-axis, x-axis, we have where this ellipse is oriented. So we used variety of models, and for that we calculate this. I did this for two cases, for when we have all the data and when we remove GLT, because we wanted to see how much GLT actually helps. So from that, it's clear that overall the widths get narrower, so we have more information because of GLT. We still have the posteriors wider in the case of when it's oriented north-south, but it's still better than not having GLT. So it actually has twice longer, wider posteriors in tau, which is the ellipticity, and xi, which is the position angle of the ellipse, which is 4 times. So since there is some bias towards one particular orientation, before we actually measure the ellipticity of the M87, I think we should do, we have done some tests of different geometrical models, and we will try to figure out if there is a bias towards one particular orientation or one particular ellipticity. So we designed a lot of different crescent models. As you can see, it goes from 0 to about 0.3, which is quite elliptical, or 30%, and is in the steps of every 5%. And we oriented this throughout the 60 degrees in the spacing of about 60 degrees. Why did we do that? Again, it's fun to figure out if there's particular bias and the limitations of imaging methods. I'm going to describe directly the results. How we did that is we made the synthetic data with all these models, and then we imaged them with all different imaging algorithms I had described before. And for those images, we used VIDA that I had described before to extract the ellipticity and also the position angle. We extracted all parameters, but we're looking at only those two. And so what's plotted here is only a subset of these models. As you saw, we did 42 tests. I'm showing only here a subset of them. And what is plotted here is for each method, either the top set of all the parameters for EHTM, Smiley, and Diffie map is plotted, or the posterior for Themis and Comrade is plotted. So on the x-axis is the ellipticity, and the y-axis is the position angle of this ellipticity. And the dotted line is the true value that is of the original model. And the gray area is where if we blur the thing with a nominal resolution, then that's the ellipticity we would get. So in order to pass, we should have the posterior or the top set in this gray area. And if it's in this gray area, then it's a pass for us, and then we can trust our methods and our data. So you can see here, it's actually for most of the methods, it does pass. Only in the case when the model is oriented north-south, we cannot constrain the angle, but we can constrain the ellipticity, which is also was expected from the feature information analysis. So now that we can trust our methods, we can now measure the ellipticity of M87. And we did this for all methods, both bands. Both bands have slightly different observational frequency. Both are also higher bands, which I described there. We doubled the bandwidth. And so for here we can see that the converged image actually looks slightly better. That's because from here on we started using spatial correlations in the prior, and also fitting for the phase gains and the gain amplitudes. But it's the same data, the same things, just the prior was changed. So here we see that the value of ellipticity is consistent across the methods, but also across bands within the error bars. And so we can average between the methods and also between the bands, and we can see it's about 8% plus 3% minus 2%. And so we did this also for the position angle of the ellipse, and it's about 50 degrees. And if you look at 50 degrees on the other direction, it's very close to where the brightness position angle is. So maybe that's telling us something. So before we even try to answer this question, why is there this ellipticity? We want to compare this with simulations, to understand this better. So what we did is we took a huge library of GRMSD models. There was 300 of them. We took only 100 because of computational limitations, and span them evenly across different spins. Because if there is a spin effect, we want them to be evenly spanned. And for that, we had some non-thermal models and some thermal distribution of electrons in the models. And we randomly selected any snapshot for this, so we don't have any bias. And then we scaled them to the size to the best mass pair, so that we have the same size for M87. And we generated data, made images from two different imaging algorithms, again for gravity. And so the natural question is, we performed well on geometrical models. How do we perform on GRMSD simulations? So for this, we can just extract the features from the images and then subtract the true values and look at the distributions. They're quite well centered at 0, meaning we can still recover the true value of ellipticity and the position angle. So since we did well on imaging, and we want to actually study the full library, and we can trust the imaging, so we just took the full true library of 300 models and performed some more analysis on this. So I'm going to describe what this analysis is. The natural question is, why am I looking at all these different parameters? So for one, our question is whether it comes from spin or something else. So definitely we need to look at what's the correlation with spin, because higher the spin, higher the ellipticity, as we have seen in the movie before. And other questions answer actually the astrophysical things like non-thermal emission or thermal emission. This is the way electron distributions functions are. And usually non-thermal models have a more extended emission, so that's an astrophysical effect. That's why we are looking at that particular parameter. There's also magnetic field state. Usually sane models are more diffused. That's why we may want to look at that. And there's also the ratio of electron and to proton temperatures in high and low density regions. That also, as it increases, has higher diffused emission. So I'm going to just quickly summarize what we actually got from these correlations. So what is plotted here is all the models in blue, and the orange is when we apply a jet power cutoff. So we have observational constraints on how much is the jet power. So we down select the kind of models that apply to M87, and so that's plotted on the right. So in all cases, we actually see the M87 in green is matching with all GRMST models. So that's not very helpful. So we look more into what are the correlations between the parameters. So we looked at the correlations between parameters, and we found that with the p-value of less than equal to 0.05, the models that have non-thermal emissions have higher ellipticity, and the models that have higher R high have higher ellipticity. So the natural question is why? Mostly because there is higher extended emission. So we'll look into actually more detail of why that could be is that the case. And the way we did that is we took all the models, fit a ring to it, and then we subtracted the ring emission. And whatever was left, we calculated the fractional emission of that. So we call that non-ring flux fraction. And we correlated that with the ellipticity value of that model. And we found that this actually is correlated with higher the non-ring flux fraction, we have higher ellipticities. So meaning the ellipticity that we see in the 28 image is actually dominated by the turbulent accretion flow and not a gravitational effect by the spin. That's not giving us the answer that we wanted, but then we can look at what we can do next. So what we can do next is we can make a video of MT7, essentially all taking snapshots over time, and then we can average out this turbulence to see what is behind the turbulence and measure the ellipticity. That's one way to do it. Another way to do it is we talked about this direct image and this other image that is the photon ring, and we can actually resolve that thin photon ring, which has a better gravitational signature, by going to space. That would give us a much higher resolution, and when we can measure the electricity from that. Okay, so after looking at what's the right way to measure spin, we can look at another way of measuring things from another source, which is Sajay. So this project is part of a bigger project in the EHT collaboration, and the main thing that we're trying to answer here is how does the black hole accretion work? Is there a way to measure spin? And I'm going to mostly get to these questions by answering the second question, which is whether and how we can trust these videos that we make. So among all the series of papers, I'm only going to talk about the one that I led in this big project. And so the natural question firstly is, why do we even make videos? Okay, and so I've already said this many times, but I cannot reiterate more that these videos are really the next big thing that we can do to understand black hole accretion and also spin. And a good source for this is Sagittarius A star, because it varies at the time scale of seconds to 2 minutes. So we can make a video out of it. But the issue is that it violates the principle of aperture synthesis that I mentioned before. That the source should be static, and the way it violates is if you just look at the coverage, instantaneous coverage, you can see it's already very sparse. But while the coverage we're sampling this coverage instantaneously, the visibilities here I'm showing only the amplitudes, they're also changing. So so we need like algorithms that can do dynamical imaging rather than just taking a static image. So because of this, we actually developed new imaging algorithms that deal with this extremely sparse instantaneous coverage. And to tackle this, we actually have many new algorithms. I'm going to just like quickly point out this Kine, which is based on neural networks and learns the correlation from the data. There's also Resolve, which is another Bayesian method that also learns from the data. And there are other RML-based methods that have different sorts of either explicit regression or just snapshot. We also have like just geometric modeling done, that's snapshot. And so for these methods, we need a way to actually like evaluate the videos. We made the videos, but in order to trust them, we need to develop a systematic framework that can find out all the potential biases that we can have in the imaging algorithms, evaluate the videos of these tests and also of Sagittarius A star, and then we can refer physical properties from these videos. So I'm going to talk about this framework which I developed called EHT eval, essentially EHT evaluation. And this framework is actually now ready to be used for any future observations. It's set up that way. And as I had mentioned before, this work is just part of a bigger project. And I want to really mention all the huge effort gone from the EHT collaboration towards calibration of the data, towards imaging, and also understanding what we're seeing. And I'm going to mostly focus on how to validate and evaluate these videos. So to do so, I'm going to describe this framework called EHT eval. And the way this is designed is throughout the validation and the evaluation, we put up series of challenges and call that a validation ladder. And each step or the rung of this ladder is designed so that we can probe what is the limitations and biases of each method, or the strength and weakness of each method. And we actually did this validation ladder at being agnostic to how they work or what they are best at. And I'm going to describe what that ladder is. So we put up a series of questions, and for each question, we created a model, and then we test how they work on these, how they perform on these models. The first natural question is, for a dynamical imaging, do we introduce additional dynamics to it, or we can recover something that is really static? So to do so, we actually just made different geometrical models. Again, because they describe the visibilities of Saj closely. And we are going to look at only the on-sky models, meaning there is scattering from the galactic center. So we're going to look at after the scattering is applied. So these are the same models that were used in the previous papers, but we also varied different kinds of polarization structures in them. That's one part of the ladder. The second part is actually a different question, which is if there is orbital motion in along the ring, then can we recover this orbital motion? And then do we have a bias towards a particular direction? And for that, we made these two models where there is a Gaussian, which is we called a hotspot, that is going around the ring, and it has some periodicity, about 80 minutes. And then we also have the counterclockwise one. So if we get both of them right, then we don't have any bias. But other than that, do we have a bias towards getting coherent features, or can we also recover incoherent features? So that's third part of the ladder. And here we, oh, sorry, this one. Yeah, so for this, we just take a Gaussian hotspot that just jumps from one location to another without any periodicity to it. And then another question that we can ask is, other than incoherency, what if the hotspot is actually going across the ring? So not something orbital, something maybe non-physical, but we want to really test that we have bias towards being on the ring. So for that, we have two models. One of the models actually goes across the ring. The other one actually goes outside the ring, and it's off-centered from the center. And the periodicity of this off-centered one is actually 180 minutes. So we also test different periodicity. Another question that we can ask is, okay, we only change things in Stokes' I. What about the linear polarization? So since there is variability in the linear polarization as well, we added a new model which has a polarization that is tangential to the ring, more polarization in the hotspot of the Gaussian rather than the ring itself, and then another one where the EVPS, or the electric field vector position angle, also just rotates counterclockwise. So in this, there is no hotspot. Just it rotates counterclockwise. The last most important question is, okay, we did good on, if we did good on geometrical models, how do you perform on realistic physical models, which are the GRMST models? And for that, we took models from this library called Karma, and then we chose the models that were previously favored by other data for Sagittarius A-star. And for these models, we actually match the variability to this data that we're using, and made sure that the light curve or the flux is matching with what we have in the real data. We also rotated them to have the visibilities matching with the real data. And on top of that, we also introduced a new model. Just out of curiosity, what happens when we add a Gaussian on top of these GRMST models? Because these GRMST models themselves cannot really produce such a localized coherent features, not all the time at least. So for all these tests, we also designed some other extra tests that is not meant to be a test of validation, but to push our limits and see to which extent we can actually recover things. So for that, one question is, how fast can we recover things? How slow can we recover things? But other than that, how bright things are different to each other. So the brightness ratio between the hotspot and the ring could also matter. So that's another thing that we test. And then we also push another limits in case of GRMST models, where if we just choose unfavorable parameters based on previous constraints, how do we perform on them? So some of them are actually quite difficult, where there's like the inclination of the black hole is almost 90 degrees, so this bisects. So these are just to test our limitations to the maximum. And so for all these models, we actually, I'm going to describe quickly how the data was generated, so we know what kind of corruptions are there in this data. And so we just use the same kind of data that has been used before in the previous PhD papers, but to just quickly summarize, network calibration means the flux of the data is actually calibrated, and decal means the D terms are also, the leakage terms are also calibrated. So we use this data for any model that we have described before. We add both diffractive and refractive scattering. And then since the real data is also corrupted randomly in phase, we corrupt the phase as well. And for amplitudes, we just, based on different calibrator sources, where we already have images and the gains, based on that, we draw some gains from a distribution with the widths that are similar to that calibrator's gains. And then we also add thermal noise. And then because of thermal noise, we also actually calibrate the flux again. Before doing imaging, we do a minor time averaging of 60 seconds. So there is actually thermal errors, and there is also phase corruptions, amplitude corrections, and also on top of it scattering. So for this data, we are going to look at one particular application of this framework, to see how the imaging methods actually performed on this particular model. So I described series of many different models, but we're going to look at one of them just to show the application. And so here we are looking at this ring plus hotspot model, where the Gaussian is going clockwise with a period of 80 minutes. And you can see that the static component actually is recorded quite well with by almost all imaging methods. Static component is the median frame of the video. The dynamic component is when we subtract this median frame from the full frame of the video of each frame. And what we are seeing here is that some of the methods actually perform very well, and we are going to use some tools to see how well they perform to see the tracking of this feature. We also can look at the visibility variance, which is essentially what is the standard deviation of visibilities divided by the mean visibilities, to see how well the variability is matched with the truth. And for some of them, it's actually quite identical to the true value. So next we will look at actually how to even call it good or bad reconstruction. And the way we do that is for the dynamic component, which is the most important one, because static one, almost everyone can get right. Dynamic one is more difficult to get. So as I had described before, VIDA, so we fit Gaussian to this dynamic frame. And then for this Gaussian, we plot things like what is the position angle from the center, what is the distance from the center, what is the size of this Gaussian, and we also look at what is the flux of this Gaussian. And we set some arbitrary reasonable thresholds for them for the methods to pass. And then we can see within this threshold, what percentage of the frames are passing this threshold. And our very bare minimum threshold is if it's more than 50%, then we call it a pass. And we can see that most methods get everything right, but getting the flux right is only for two of these methods, with this EHTeam and Kine. So that's how imaging methods perform. But we also have modeling. And for modeling, it's snapshot modeling. So we can also get posterior, since it's a Bayesian method as well. And you can see the red dots actually are the true value of the position angle of the Gaussian, and the blue distribution, the histograms, distributions are of each timestamp, what is the parameter of the position angle. And you can see that it misses sometimes when the coverage gets bad, but overall it does quite well, especially in the green region where we have better data. So other than looking at the feature extraction of the Gaussian, we can also look at the cross correlation of the each frame. And for that, we just cross correlate each frame and see how many frames, what percentage of frames are above this threshold. And for that, we can see there are three of the methods clearly above 50% of the time having good cross correlation with the truth. So that's another metric that we can use. So we are using so many metrics to see if we can actually do overall well in all perspectives. Another thing that we can calculate is the pattern speed that I described in the beginning of this talk. And for pattern speed, what we do is, again, we calculate the radius mean across the time. And then along that radius, we slice the cylinder plot and calculate the pattern speed. So for getting the error bars, we actually use different errors from the radius, and also different kinds of threshold in the autocorrelation function to sample in MCMC to get these error bars. And you can see within these error bars, almost all of them get the pattern speed correct. So we saw that we got the features of the Gaussian correct in some methods, the cross correlation in some others, and then some small subset of them, not some others, and then all of them get the pattern speed right. So we have series of number of tests that we did, and now we can look at the summary of them. I'm not going to describe each different model that I described before, but this is too big of a table to read. But essentially, what we do is for all the different tests I described, the cross correlation, the pattern speed, the feature extraction, we calculate the total number of tests for each question, the static models, the dynamic models, and the GRMHD models. And then we see what number of tests actually passed. And then if the number of tests are more than 50% for each question, then we call it a pass. And you can see there is at least one method that is passing for all the tests that we designed. And there are two more methods that come very close. They fail only when the things get difficult in polarization for more realistic model like GRMSD. So we have at least three methods that perform very well. And this sets up the validation ladder that now we can trust the real video of Sajid. Obviously, I'm not going to show the real video, but this framework is really sets up to start trusting our real videos of Sajid Star. So now I'm going to start concluding all the things that I've described throughout this presentation and what we can look at next. So firstly, we looked at this newer data, what things have changed. And throughout this thesis, I've also tried to bridge the gap between the data and the interpretation. So we have different methods developed for this interpretation. And one of them is imaging and feature extraction. So the big contribution was to image with Comrade and get posteriors, both for images and telescope calibration terms. From doing this imaging, we confirmed that the ring is of the same size. We confirmed that we discovered that there is a shift of 30 degrees in the brightness position angle, which was a direct view towards the accretion dynamics. And then we also looked at the ellipticity of this particular image. And we found out that this ellipticity of 8% that we got, which is 0.08, it's actually an effect of astrophysical effect and not a gravitational effect. And then we set up the future step as we'll go towards making movies or making space observation to see a gravitational signature. The third contribution of this thesis was to validate this first video of horizon scale video of Sagittarius A star. And by doing this particular project, we actually develop a systematic software or framework to validate any horizon scale videos in the future. So in the future, any EHT data or any other data we would have, we could just outrightly use this same framework in the future. So secondly, a natural question that you might have is, okay, this is a lot of work in EHT, but what is the broader impact of this work? So firstly, I would like to point out that this Comrade imaging algorithm that I mentioned before is not only used for imaging black holes, but also jets. So getting uncertainty quantification can be used for any other arrays as well. So and we can not only get the uncertainty quantification for the images, but also for the calibration terms. Secondly, by doing this imaging, we actually provided some theoretical constraints on our models, observation constraints on our theoretical models. And thirdly, this validation framework that I developed is not only applicable for videos, but also for images, and also beyond EHT, not just EHT. So because the tools are very standard. So lastly, I would like to conclude with the future looks actually quite bright, meaning that we have things like next generation event horizon telescope, where we would have a lot more telescopes, a lot more coverage, and hence higher fidelity videos. Secondly, we have space missions coming up to resolve even finer details like the photon ring and get a cleaner probe towards the rest of GR. Thirdly, we have multi-frequency observations that are coming for horizon scale. And through that, we can make posteriors of spectral index maps and Faraday rotation maps to better understand how the jet launches from the black hole. And lastly, the big thing that is probably coming up is the M87 movie campaign in the next few years. And for that, developing an algorithm that can not only give us videos, but like a posterior of velocity fields that are more physical to understand. And we can use that to robustly understand the black hole accretion and also jet launching. That's all.
Thank you very much, Rohan. So that concludes the first part of the thesis defense, and so now we'll move to the second part, which is going to be a round of questions by the committee members. And we'll start with Kute, who's the secretary of the committee.
Thank you. Yeah, thank you for the nice presentation. It was very clear and actually clarified a lot of doubts that I had when reading the thesis, which was just a few general questions. Especially, I understand well the topic where you most worked on. I understand was the last one with the video validation. It was entirely yours, and but in the first part, the imaging M87 with Comrade, which was where you are the co-author of the whole collaboration. What was actually your contribution?
So yeah, I'm going to put back the slide so it's easier to understand. So my contributions start from the fact that when we get EHT data, we have to look at how well the calibration is done. So we do a lot of tests, and all the tests that I describe actually here. So I did perform all these tests, and this is actually the last version of the data. But before that, we found out any data issues. So I helped in that. And then I actually led the imaging with Comrade. So image that you see here is contribution of mine, obviously with the help of the original developer Paul Tida. So I made these images, and on top of that, I also helped with looking at what are the posteriors of the gains with the synthetic data test and also the real data. I also looked at what's the compact flux of the source. So because in Bayesian methods, you can also get the posterior of that. So essentially, my most contributions, I would say, would be finding data issues to making images, and then also writing the paper and discussing with what the physical interpretation is. I did not do the physics part of it, but I was involved in the discussions of it.
Also involved in writing part of the paper?
Yes, so the Comrade part and also some appendices are written completely by me.
And in the next publication, which where you are the first author, I understood that the largest part of the work has been done by you.
So it's a co-shared paper. It was primarily led by me, but it was also led by Ilje Cho, who was in our group here before, but he is in a different institute now in Korea. We both led this work, and it involved actually quite a big team. We have about 20 authors that worked actively, and then the rest of the collaboration commenting on the paper later on. So the paper looks like 276 authors, but the original contribution was from of us, and mostly also I was the one who wrote the project proposal and came up with the idea to do this project.
With respect to the last chapter with the video validations, so that's a very nice and complete work. What is actually, you said you're developing the software. How can one imagine that the end product looks like? Is it something, or well, I have two questions actually. Is it something which is going to become public as well, so that other people can use it? And how can they use it? How does it look like? Like a program?
Yeah.
Some input and get some out.
Sure.
Which you document and.
So technically it is not public yet, but when the paper comes out, I do plan to make it like open source software. And so it's actually based on EHT imaging software, which has all other tools like loading images, loading movies, and also extracting the radius and all of that. It also uses Julia. So EHT imaging was Python. It also uses Julia for feature extraction from Vida. So it's a series of scripts that will be organized in classes. And so if you want to just, let's say, generate data for one particular model, you just define the parameters and let's say generate data. So you would just generate data. So that's how easy it would be to generate data, because for now you have to look at huge scripts and understand each parameters, but it would be made easier with just one function for that. And then for evaluated, so it's an evaluation script. So if you want to evaluate what's the cross correlation, how well the things are tracked, what is the percentage of frames passing. So for that, it's just parameters that you can just turn on and off to see what thing should be tested. And for each parameter that is turned on, you get a plot and also a CSV file that you can just look at and evaluate each different aspect. So it will be coming out as easier functions to use rather than writing your own scripts, and also notebooks to run this easily and understand them.
So, yeah. And, okay. So, and you said that in the future, you're going to, well, extend this program, these methods to more complicated targets or to multi-frequency data. Do you expect any differences? I mean, what do you think you will need more complicated models for that, or how do you think you have to extend your model?
Right. So I've been mostly for imaging, I've been using Comrade, for example. And Comrade can do full Stokes imaging right now. It has started to, so I actually developed the background for doing the Fourier transformation in frequency and in time domain. And then this work was taken up by another student who added the priors for the spectral index maps. And then my next step would be actually to add priors in the time domain, because when you try to sample in time domain, it's extremely computationally expensive. So you need to actually port this to GPUs as well. First thing would be to define a prior in time domain, and the second thing would be to port everything to GPUs. So these two developments would be required for that. Now, in order to get velocity fields, I was actually starting to look at work from Aviad, who has done this before, where he used Gaussian random fields to get the velocity fields. So we already have very good method called Kene that actually gets very nice videos, as you've already seen. It works very well. But the things that are pending is it still cannot give you the posterior. So it's not Bayesian yet. So that's pending. That can be still also included in Kene. But in Comrade, since you use Julia, it's also faster to do so. Another thing that you would need to add is the prior to actually get physical velocities. So you would probably have to use priors that are will work mostly on black holes initially, because if you use priors that have velocity fields from accretion disks, so you would easily recover accretion disks, but then recovering things like jets would be difficult. So then you would have to use different set of priors for jets. So my personal intention is to develop something that is Bayesian, so you get uncertainty quantification, to get a video that is correlated in time, but also has posteriors of videos. And then lastly, this would have to be developed in a more physical way to understand things. So we can make videos, but then after looking at the velocity fields or videos, to understand and compare with the simulations to better constrain the physical models. So that's what I would like to work on. Yeah.
The ideas I see. Good. Finally, the paper is in preparation, and how long do you think it will still take?
The last one?
Yeah, the last paper.
So the paper is already written.
Okay.
That's also part of the thesis. We are expecting some final things to understand what exactly is going in the real video of Sajay. And since this is a bigger collaboration effort, we have to converge on the theoretical interpretation. So we expect in the near coming months, not in summer, but after summer, to submit this paper to the journal. So I'm just waiting on the other papers to be ready. Yeah.
Also the other papers to catch up.
Yes. So.
Okay, thank you.
Okay, so now my round of questions. First of all, let me praise you a little bit. I think this is really excellent work. I think you are working in this very exciting region on the interface between methods of image processing, methods of advanced statistics, and radio astronomy. And this is something that radio astronomy really needs to be more quantitative and to be better and more rigorous with that respect. Also the evaluation of errors and so on. So kudos, this is a great contribution to that. And furthermore, as a member of this large Event Horizon Telescope collaboration, well, I thank you for your huge contributions to the collaboration projects, and I hope you will get appropriate credit for the work where papers are authored by 300 alphabetically ordered authors. All of your papers have actually that you
Yes.
apply for this work, 300 co-authors, but for one of them you are leading. Okay, so now as is the custom, I need to grill you a little bit. Presentation was also excellent in my opinion, and I found one grammatical error that I will not even bother to mention without.
It is highly likely.
It was violating the assuming of apertures in the function.
I thought I fixed it.
We fix it in the next slide.
Yeah.
Previous slide. You introduced closure amplitudes as log closure amplitudes, but it was the equation for closure amplitudes. But I'm aware that you are familiar with works of Napier from 16th century, and you know what logarithms are.
Yeah.
Like no doubt. There was one statement in the slides that was not entirely wrong, but also wasn't entirely right, or at least was imprecise. So this will be my first question. So that was where you introduced R high and R low,
Yes.
and you wrote that these parameters differentiate different density. Oh yeah, that one. R high and R low are ion to electron temperature ratios related to high and low density regions. This is true, but it is not precise. Can you describe more what is this a higher low prescription? What is it? What is it doing? What parameterization it takes? What physical quantities is it sensitive to?
So, so R high and R low are actually not independent quantities. They are in the part of the same equation where it relates to the temperature of the electron to the temperature of the proton, and R high refers to this ratio in the regions which is close to the more extended part of the source. So and R low is towards the more inner part of the source. That's what I understand basically.
Parameter that it use equation for the temperature. It's not what physical quantity. It's not density.
To be honest, I am not well aware what exact parameter it uses.
Plasma beta, it is proportional.
There's alpha and beta, but I don't know what exactly alpha and beta in those equations I really refer to.
Okay, that's okay, because plasma beta is correlated with density. It is a ratio of pressures. The
Right.
pressure of gas versus the pressure of the magnetic field, and the pressure of gas is proportional to density. So this is, as I said, it's not really wrong. It's just imprecise. So I'll let it.
I will fix it.
Okay. So then another question I have, there are so many methods that were used for these reconstructions of images, and I counted 8 methods for this 2018 paper. Can you paint like a landscape briefly? What are differences between these methods? How do they work? Are we duplicating very similar algorithms, or are they very different algorithms?
Yes. So as we do in EHT, we do a lot of redundancy to make sure that whatever we are doing correctly. And so that's why we use a lot of different imaging algorithms, as you are also aware. They are not exactly identical methods, though. They have their own differences. So for example, diffmap here works on the assumption that you just replace the source by point sources and then convolve with the convolution beam. So it's a more inverse approach of doing a direct Fourier transform. And then EHT imaging and Smiley are more or less similar, but they have a different way of regularity, using different regularizers and sparsity. So this actually is a forward approach where you define the image and then you try to minimize after going from image to visibilities and minimize the difference through an objective function. So these two are similar, but they have their own way of defining the regularizers. Then there is Themis and Comrade, which are both Bayesian methods, but they have their own differences. So for example, in Themis, there is it uses a very small grid of pixels because of computational reasons. And there's a lot more variable parameters, like also the grid rotating and moving. Other than that, it uses extremely sparse pixel intensity, so that like it doesn't fit for too much diffuse things. It looks for mostly the most sparse things. And in Comrade, we use independent priors on the pixels, so it actually puts the flux array for this particular work. We use independent priors, so it puts the flux wherever it can fit. The difference between these two, that the biggest one is that we can fit for the posterior of gains in Comrade, while in Themis you just optimize for the best fit gains. This is extremely fast, Themis is extremely slow. So that's one advantage of using two different ones. And in modeling, so it's the same thing as we have. So hybrid Themis is actually essentially an image grid behind it, but on top of that we fit a ring, so we can have a more sharper feature, and also it's faster to do so by using a geometrical thing. These two things are actually from Comrade, two different models. One of them is crescent with a Gaussian, the other one is another Gaussian dispersed ring. So they are just two different models. But actually, no, this one is just a geometrical modeling of Themis without the image part behind it, and MF ring is the Comrade one. So they are all done in a different way. They have some common features, but redundancy is good when we are dealing with such sparse data. That's what my answer would be.
What would you say is the biggest advantage of content that you are using?
Biggest advantage is compared to Themis, in this particular work, you get calibration terms posteriors. Second biggest, it's way faster. And yeah, for this particular work, I would say these two. There are more in the future.
So another question is, so this first project relates to search tires A star and evaluating synthetic models,
Yes.
the performance of algorithm. And the problem with this source is its variability. So can you discuss a little bit, so why is Sanjay so variable? What are the timescales involved in that? What is the source? Is there an identified physical source for this variability? What process manifest through that, and what is to learn from studying variability of such values is there?
So firstly, it's 1,000 times smaller than MT7. So a matter can go around much more faster because there is less distance to cover. So it's faster that way to go around black hole. Secondly, it has a lot of interaction with the nearby stars as well and the interstellar matter. So that's one thing that makes it more interesting. Thirdly, um, this source also, from a multi-wavelength perspective, has flares going on in let's say X-ray that may have connections in the radio domain. So we want to understand how the multi-wavelength picture looks like for Sajay. Regarding what exact physical processes go, I wouldn't be able to answer more than that, I think, unless you point me in a particular.
To do something turbulence.
So it's smaller, so there it's more turbulent. There's also the accretion rate is much higher than MT7 as well. Since the accretion rate is higher, so that's why it's more turbulent.
Rate is actually low. What is the time scale involved? Is it matter going around? So what is like?
When
Can you name like the orbital time scale?
seconds to minutes order, I would say it's 20 seconds to.
There are like at least two different things. There light crossing time for some how fast light would cover per particular distance, and there is a time scale like dynamical time scale how fast matter.
Right. So the light one is more straightforward. You can just check the size of the black hole and then calculate what it is, and it would be the order of seconds. And then the other one is the order of minutes. Yes.
Half an hour for fortune, but it will be few minutes
Yes.
for the black hole. Also, Okay, so that would be my second question. The first one is kind of specific about the paper that you led. So you showed comparisons with GRMHD, and I noticed that you had ellipticity there, but I didn't see the angle. And I understand that from the data you extract both ellipticity and direction in which the image is elongated. So my question is how does that work in comparisons to GRMHD? Are the GRMHD models also finding this particular direction of elongation?
So we actually just randomly rotated the snapshots since we were not interested in them. But other than that, I also checked the similar plots for the position angle, and it doesn't have any correlation for a particular angle because there is different kinds of model and also different snapshots. Depending on snapshot, it changes the angle.
Okay, I see. So in the paper you don't try to
We
extract-
don't explore this parameter. We just randomly rotated the models.
That's another cool thing that maybe for a follow-up or something. Okay, so that was my first question. Thank you. And I will not go through all the questions I've written down, but like let me ask like at least like two more. Okay, so another thing I noticed you referred to GRMHD simulations as realistic, which is goes getting to some people and like like we use GRMHD as sort of a compromise, computational compromise for how advanced are our methodologies, so that we could make comparisons to data with like big collections of models. But so I'm absolutely not against doing it. But I would say a sentence that will be technically true, and I would like you to elaborate what I mean by this sentence. So if I say that GRMHD simulations are solving wrong equations with dubious initial conditions, with insufficient resolution to capture some physics that is going on. Could you offer a comment on these three aspects, like equations that are being solved, initial conditions, and the resolution?
Okay. So, equations, there is obviously the GR equations, and then there is the fluid equations.
The other part is probably set.
Yeah.
But
And then
MHD
there-
part, magnetohydrodynamic part,
There's Maxwell's equations, and there is also the
Maxwell are also probably fine.
Yeah. So the fluid part is, I think the problem is conservation of probably energy or momentum, that we have to reset after every few epochs. In these simulations, we have to reset that back. And that's one of the problems with RMG simulations.
This is one of the problems.
Yes.
I wouldn't say this is the main problem. I will lead you a little bit in the direction of the answer. So you mentioned that the mass accretion rate is very low in these systems. It is lower if time is like 57 actually. And well, then the density must be low. So an MHD is a fluid equation.
Yeah.
Is it a good assumption?
Well, the more less the density becomes, we are more going towards the gaseous state. So
Okay.
it's more going towards the gaseous state than just calling it fluid. So the interactions between, to call it a fluid is itself violated as we go lower and lower in the density. So
Interactions is the key word.
Yeah.
It's not a fluid. It's collision. We call it collision.
Collision, yeah.
For a reason. It's not colliding. The species do not communicate with one another, but cannot behave like a fluid. So that is a part about like the first thing. Now, the initial conditions of GRMHD. How do we start this simulation? This is reality.
Well, I will have to recall what do we start with? What are the initial conditions?
Start with like a torus or fixed angular momentum. Is this something that anybody's seen ever in nature?
fixed angular, well, angular momentum is itself variable. If it's a torus.
Well, the direction of the angular momentum, right? It's not coming, gas is not coming from random directions, it's coming from an equatorial plane. Is this a realistic assumption?
No, because there is interaction with other parts of the media as well. So
You also mentioned something about Sagittarius historical interaction.
yeah, there are other stars and other interstellar medium that is interacting, and so matter coming from one direction itself is probably not realistic.
Stars are not really aligned. So
Yeah.
perfect. That's exactly what I mean by that. So now the resolution, the last of this, only few problems with GRMHD. How about this resolution of the
In
simulation?
time or in space?
Oh, let's say in space. Is there physics that is happening
So
below the scales of?
so when we do numerical integrations, the size of the integration, the pixel, should be smaller than a particular quantity, which is based on the momentum as well, and the, that probably is used correctly unless there is computational limitations and we have to use a bigger pixel than that. I don't know if that's the answer you're looking at.
That's quite related. I like the clearest answer would be, well, reconnection physics, for instance, all the physics that is happening on the scales below the grid. All the dissipation of energy happens on the smaller scales above the grid. It's an effective one. This is why we need things like this beta prescription with R high and R low that you mentioned.
Yes, but I would assume that we are not going at those scales because of computational reasons. Yeah.
Oh, yes,
Yes.
CBT, absolutely, we cannot do it, but it doesn't diminish the criticism of
Yeah.
the method that we are not doing something for the reason that we cannot do computation.
But there's also works from Bart Ripperda who looks at ultra high resolution of these to look at magnetic reconnection. So I would assume that's what you're referring to.
Absolutely, yes, exactly. This is what shows the very different behavior on a small scale. But the question how much it matters for the effective behavior of the system is kind of an open question. Okay, this is awesome. Thanks. So I will ask maybe one more question and maybe does it. So let's get back now to VLBI and the techniques. So you mentioned many different errors, kinds of errors in this that we are sensitive to and we need to. You see no longer here. That we need to take care of. Let's just name three types of errors that I saw in your presentation: the thermal error, the gains-related errors, and the leakage errors. Could you just give us a short introduction? How do these errors originate? What are the characteristics? Just describe it a little more.
All right. So let's start with the amplitude gain, which is this G parameter here. It could come from two sources. One, the measurements that is happening at each telescope has a particular system temperature that would add some gain to it. On top of that, we have opacities and the atmosphere that is corrupting the amplitudes. So each site will also have time dependent corruptions to the visibilities because of the instrument and also the atmosphere. The leakage one is an instrumental error, not an atmospheric, where we are measuring the circular polarization and the right one and the left one. So the signal can leak from one probe to other probe. That's the leakage that we're usually this one is a constant over the course of observation. So we just solve for that particular observation and fit for that. Don't fit it for the whole time. And there is also station-based errors because we are correlating, and when we calculate the closure phase, there's triangular 3 or 4 telescopes involved. So there's non-closing errors that usually are not dealt with in any of these that we add as systematic error to our data before imaging. What was the third one? I think this is.
I mentioned thermal error.
Yeah. So thermal error is just part of the instrument that we're using, and that has the electronics that corrupt the signal. So that is the instrumental error.
How to make thermal errors smaller.
Cooler cryogenics, cooler things.
Okay, so that's one way. what, like size of the dish?
So yeah, you can make it bigger and bigger. Dish is more sensitive, and so hence less the thermal error.
Okay.
Yeah.
So I will actually ask the last question.
Yeah.
That will be the last one. So could you, the phrase shadow happened a couple of times.
Yes.
And it was, seemed to me a bit in different contexts.
Yeah.
The whole image was a shadow, and there were these narrow lines in one slide that were a shadow. Could
Yes.
you define with maybe some caveats what is the shadow? Let's stick to that. What is the shadow of a black hole? Just describe it.
So it is defined as when the photons are going bent around the black hole, but that's the last orbit that you can have before it cannot escape, and that forms the boundary called the critical curve of these photons. And these when we project it on the screen, that region where it doesn't have any light or photons is the shadow. So the last orbit where it gets bent is
What feature in the metric, what physical radius is it sensitive to?
it's the few times the Schwarzschild radius that it is. So it's about, I think, root 27 times the Schwarzschild radius where we form the shadow
In the image,
in the image. Yes.
around the black hole. How this final orbit of the photon, or well, the only orbit of the photon, how do we call that?
Photon shell.
Photon shell.
Yeah.
Perfect. Okay. Well, thank you. That's it from me. Thank you very much.
Okay, so I guess it's my turn. First I want to second, Maciek did some grilling, but before that he gave you a lot of compliments. And I want to second all of these compliments. And I think, you have a thesis title. I want to give it a subtitle, which is really about your thesis. I really see it as about how we can rigorously build confidence in EHT results and in the follow-up scientific interpretation. So all of the work here is about uncertainty, is about evaluating the models, is about building confidence in EHT results and the science, which is super important. And I want to highlight that you did. So we've been working together on the dynamic imaging part, so the third part of the thesis. And there you are part of a very small elite group of students that are, single-handedly lifting this whole project. So really fantastic work in all aspects. So you also are, your work is very unique because it's, much I've already said, but it's cutting edge both computationally and astrophysically. And so since you spend a lot of time grilling the astrophysics, I'll take some time grilling the computational parts. And so let me see, I have a few questions here. The first is a slightly technical question, which is, you talked a little bit about the fact that Comrade uses HMC sampling. And I don't remember if also Themis uses HMC sampling, but maybe it does. But either way, you mentioned kind of very briefly that HMC helps probe multiple modes. Can you maybe elaborate on this and clarify this?
So okay. So firstly, Comrade uses HMC, but Themis also has different types of samplers, and one of them is also HMC. And the way HMC works is it calculates this acceptance rate based on where we are. So let's say we have one of the posterior here, we will calculate the probability there, and then also the slope, the energy because of that slope of the posterior. And if we are far away from the bimodality, so there is a dip, there's a peak. So if we are far away, we will sample this well, but at some point, because the slope tells us to go on the other side, as we go towards the lower side, it becomes flatter in terms of the slope. So it jumps on the other mode because of that slope. And so then it samples the other side by measuring how much is the energy at particular slope.
So to clarify, essentially you're saying that it senses that you're in a local minimum.
Yeah, it senses the
and
local
it will
minimum.
have some radius to jump.
Yeah, so the radius to jump actually gets larger as the slopes decreases.
I see.
Yes, because of that, it jumps to the other mode. And if the radius is smaller, then it just samples more and more. So if there's a peak, it will just stay and keep the radius of the acceptance smaller and keep sampling there. And once it goes to a more flatter thing, then it will increase the radius to jump to the other side.
I see. I see. So that helps if um but still all the operations there are local, right? You compute derivatives, and you figure out this posterior at one single point and the derivative at that point. So you can still get trapped inside a single mode without ever escaping that mode.
You can reparameterize it. You can always reparameterize your posterior so it gets easier to jump. But if there is an absolute dip, it's more difficult to bigger the dip, it's more difficult to jump over any sampler anyway. But for HMC, it's easier than just Monte Carlo sampling, I would say.
I see. Okay, great. And so on this line of MCMC kind of questions, so how do you know that the chains are actually converged? So one critical thing about MCMC algorithms is that they promise us that they sample from the posterior at some unknown point in infinity. How do we know that we're there? How do we know that we are sampling the posterior?
Good question. I like this question because I will answer this question with bees. So if you have a house with multiple rooms in it, if you release like one bee and you just moves around the whole house, and if you can track where it went, then it's not well sampled. But at some point, if you release multiple bees and then you cannot distinguish between what bee took what path, then you know that you have really sampled well the whole map of the house. And so essentially means that when you cannot distinguish between different initial starting points of the sampling, then you know that you have been everywhere around the posterior. The way you can calculate this mathematically is using either a thing called effective sample size, which is if the sampling was independent, this is dependent sampling because we are looking at a particular location and stepping to the next one depending on where we are. But if we were to do an independent sampling, and the results were the same of the posterior, independent sampling would take a lot of time to sample. But if it had same results as the dependent sampling, then it's well sampled. There's another quantity called R hat, which quantifies how well these different multiple chains look similar to each other. And if it's relatively similar, then it's usually considered less than 1.1 is considered as well sampled posterior.
I see. I see. But going back to the bees are exploring a three-dimensional or map, and you're exploring
I took
maybe
a two-dimensional.
million-dimensional. I don't know how, maybe 100 pixels by 100.
Yeah,
very high dimensional.
probably very high dimensional thing. Yes.
Is there any difference? So do you expect this to work the same on whether you're exploring a million-dimensional space or a three-dimensional space?
It would just get slower based on the number of dimensions, but the results would be the same. It would just take longer to converge depending on how many dimensions we would have.
I see. Okay, great. So touching more a little bit about uncertainty. So you have this picture of well, okay, before I get to the uncertainty, you have the results of the synthetic data. Yes, these results. And
Yes.
both MS and Comrade have this ring substructure that looks like little blobs. And I'm just wondering if you could give us some intuition of where this coming from.
Two reasons. I will answer with Comrade and then Themis. The first one is this image that is shown here is just the maximum posterior image before doing any sampling. This decision was taken as a collective thing from the collaboration to put this for Bayesian methods, but the right way to represent an image for Bayesian methods is looking at the mean image. And if you look at the mean image, these blobby things are much more smoother because there's other things that would cover up the gaps and make it more smooth. Secondly, it also depends on the number of pixels you use. In Themis, we use very little pixels. It's 5x5 grid that makes it more bloppy. So usually when we look at Themis results, we should just blur it to some beam before we even conclude anything from that image for Themis. Now, in the case of Comrade, there is another issue for this particular paper that we introduced no correlations between pixels. So sometimes they would get accumulated in one particular part without having any correlation with what is going on in the neighboring pixels. When we look at these images, when we use this spatial correlated prior, it looks much cleaner and much smoother, unlike like any other method here. So these are the three reasons why it looks more blobby here. But at the same time, if you also look at the uncertainty map, the fractional standard deviation, you would see that this blobby things is not real. It would show you that what features are real, and it would tell you that the ring is much more smoother in the fractional standard deviation.
I think I'm confused by this last statement because the uncertainty, one of my questions here is, you also see these blobs in the uncertainty maps of the real. So if you go to the real, the uncertainty maps of the real M87 image,
Yes.
you also see these blobs, right?
Yes, but they're in the opposite thing. So it shows more uncertainty where we have gaps, less uncertainty where we don't have gaps. So it covers up. It's complementary. So
I see. So it's the inverse.
Inverse,
It's
yes.
the inverse of the blobs.
Yes.
Okay, I see. Okay, interesting. So, but the uncertainty. So the mean image, you're saying that it washes out the blobs because you're averaging over, maybe slightly shifted versions of these blobs and so on.
Yes.
So why is it not washed out from the standard deviation?
I need to think about this.
Okay, I can think about it later offline. Okay, great. So maybe I'll move away a little bit from uncertainty and Monte Carlo, and talk a little bit about the evaluation ladder. So this is a question, we've had these conversations before, but the key question that is unanswered is, how do we actually rigorously pick these pass fail criteria, right? And I'm not expecting you to give me like, this is how we do it. But this is obviously something that you spend a lot of time thinking about. And so I'm wondering if you can, maybe you can imagine a world for me where these are somehow picked by the statements that you want to be able to make about theory. Let's say if I want to constrain the theoretical interpretation to that degree, then these are, maybe you can imagine something in the future of how we could, just based on the thinking that you've done on the topic, how we could actually rigorously go towards rigorously constraining these threshold.
So there is two aspects of this. Constraining theoretical things would come from the real videos, Ajay. This is just for our test to say whether we did good or not. So here theory doesn't come in.
Okay, but before we continue down this path, our confidence in the real video relates to
Sure.
these synthetic models, which relates to these uncertainties. Now, the path there goes through human intervention, but I'm just trying to imagine a world where this could be made automatically and how that would look like.
Okay. So one of the things we always talk about is what is the uncertainty on our measurements of the real video. And from what I have understood is you can use many different uncertainties, but the biggest uncertainty that is in the real features that we extract from the real video comes from what biases we have from the tests. That's usually the largest error bar. So now if we want to make a claim that the measurement of the pattern speed is within, I don't know, a 10% accuracy, then we need to go back to these tests and uh, tune the thresholds in such a way that we have at least one method that would give us 10% uncertainty throughout all different steps of the validation ladder. The way we pick this thresholds, you probably are already aware, but one of the things that were kept into mind before picking up this threshold is let's be as lenient as possible. That led into more things passing and more pipelines passing. And when more methods pass, they actually have a huge error bar on things. So just to give an example, not giving all of them why we choose things. For example, we chose about 20 degrees as the position angle thing because that's about the size of the Gaussian. So when it's shifted towards the left or right, that's the biggest thing we can have as the error. Now 20 degrees means that's quite a bit. 20 on one side, 20 on the other side, that's 40 out of 360. So that's actually giving quite a big of error range if pipelines were towards the very edge of this to pass. That's 40 by 360, 1/9. So that much is the error that we are allowing. Now we want to fine tune this to have a smaller error overall. It's of course not as straightforward as doing just 1/9, but if we make this smaller, then overall for all the tests, the error would go down. Yeah, so that would be my answer. So if we have to tune it, we would have to tune it in such a way that the deviation from the truth has such an uncertainty that when we look at the deviations from all the validation ladder, only the pipeline that has the least deviation passes, and then we have hence more constraint on the real video and hence more constraint on the theory.
Great. Maybe I'll ask just one or two more questions. So again, one question is about well, looking at all of these works consecutively, you can't help but notice that Comrade is not part of the dynamical imaging methods. And I'm wondering, how would we scale Comrade to work for dynamical imaging? And what would be needed other than, we need to buy better GPUs and things like that?
Well, we can always do things like that are already done by other imaging methods. For example, Resolve. It uses Gaussian priors, and since it uses Gaussian priors on every single parameter, that is just nested Gaussian processes, we could use that as a prior and easily make Comrade as the Julia version of Resolve and do the sampling on a GPU. Let's say we have access to GPU, everything's ported on GPU, we can use the same prior. So there is a way to make it Comrade easily ready to be dynamical imaging thing. You can also just like port the whole Kine network architecture as the prior for Comrade and call it like the Kine.jl. But there's no point in repeating things. I would say things that are already working, we should just use them as it is. We should do something new. I could have implemented this directly as what Resolve does, but I think what would be more meaningful is to also have the velocity fields. We always post-process these things, use optical flow to get the velocity field. But I think if we can have something more physically meaningful, that is the reason why it was not developed in this direction. But if you want to do things like geometrical modeling, there's already snapshot geometrical modeling, but now Comrade is ready to just introduce simple priors between geometrical timestamps nearby timestamps where you just use like a Gaussian distribution to correlate them in time, and you can have like a geometrical model that is correlated in time. That is very easy to implement. But to get a velocity field, I think it's more tricky. That would be my answer.
There are any other interesting questions here? Okay, so I have another question. Might be vaguely put, but the question is, you've introduced in the last part, you said you guys introduced correlations into Cormorant
Yes.
For the 2018 data,
Yes. Well, for the ellipticity paper, yes.
for the electricity paper. So once you introduce correlations between pixels,
Yes.
does it still make sense to visualize the uncertainty as an image, with pixel-wise standard deviation? Because now we've introduced correlation. How do we think about visualizing uncertainty in correlated parameters rather than independent parameters?
I'm going to think this out loud. So we use this Gaussian Markov random field prior, which you can restructure and write it as a summation of total squared variation and L1. So you have by changing the prior, we have now changed the way we look at uncertainties, right? This is really the weak point of Bayesian imaging. What uncertainties we claim is encoded in what priors we use. The more hard-coded prior we use, the more biased uncertainties we have. So for sure, we have gone from more independent or unsupervised, let's say, prior to a more like physically understandable prior. So we have changed the meaning of uncertainties. I would say that we are still looking at the full space of all different weights of this total squared variation and L1. So we're sampling in that direction now. You could do this for RML methods where we have total squared variation and L1, and you run a huge parameter survey and then do that, but that would still not be a posterior. But in the case of Comrade, since you are actually defining it in a probabilistic way of what would be the weights of these total squared variation L1, it's still some kind of posterior, but the meaning of that posterior is now more limited, and I would say that uncertainty is also slightly more underestimated, I think. That's what I can think out loud right now.
Yeah, maybe I could walk you through my line of thought here is I'm merely talking about visualizing the uncertainty right now. So you could think of, maybe there's a correlation matrix that specifies the correlation between every pixel and every other pixel. Now in the original formulation that you guys had, you assumed that every pixel is independent than any other, is independent of any other pixel. So this large correlation matrix actually becomes a diagonal matrix, right? Because
For correlations,
there's no cross correlation between the pixels.
Yeah, so there is
So then you can visualize this diagonal as an image. You can reshape that thing and say, I'm going to look at this as an image. Now that I have correlations between two pixels, visualizing this as an image doesn't really give me all of the information that is there, right? So how do we think about visualizing a posterior with with correlations across pixels?
But there is covariance now because it's correlated.
Right.
So we have to also look at the covariance.
So what would be so how would we think about visualizing full covariance matrix?
We marginalize in different directions along different parameters that we want to measure. We marginalize along those and look at those uncertainties separately.
Right. So one way would be to marginalize across different directions, but here directions are pixels.
Yes.
So I don't know how much that is informative. But what do people, if you have a full rank matrix, what do you typically do to investigate that matrix?
Well, we can do multiple things with it. We can calculate the eigenvalues uh, and eigenvectors, and we can project our uncertainties along these vectors to calculate what's the uncertainty for that particular eigenvector.
Right. So that was, I guess that was my line of thinking. You might need uncertainty modes in that case, or you need to have specific directions of spatial correlations that are interesting,
Yeah,
rather than independent pixels.
right.
Okay, great. I think that's it for me at this point. And so now we can, now we could have, if the committee has more questions, we can take more questions from the committee.
I just want to say that you can make an image of a full correlation matrix, but it would be for 100 by 100 pixels, it would be 10 megapixels.
Yeah.
And no journal would ever accept.
Um,
No, I'm fine.
Okay, it seems like the committee is satisfied with the questions, so I've been informed that the Spanish tradition is to ask if there is a PhD doctor in the audience that would like to ask any questions. Now is the time to ask a question. Okay, I see a question there in the back.
If I may, I'd like to congratulate Rohan. Hello, by the way. I think your work is really astounding, and I'm really impressed by how much you did in such a short time. And this should be highlighted. Your contribution, I see, is really a key in this project. And I have a question also I want to ask you. Although it's not my domain, I'm going to put it in a general perspective, right? But before I do so, I want to put it into context. So one of the most hated questions I, as a scientist, am asked is when a non-scientist asks me, what is it useful for, or what does it lead to? Because it gets always very political, and I don't know like from which way to start this whole process of convincing somebody.
Right.
So I'm going to turn around this logic, and instead of forcing somebody to throw in promises, oh, we could do this, that, I want to reverse the question and ask you, as a data scientist and as a scientist in general, do you have a feeling or a general idea of what is the minimal amount of data that you would need to be able to reach kind of the same conclusions? Or do you have a feeling of all the data that you have, right? Could you reduce it to 90%, or all the telescopes that are connected, if you lose one, could you get an idea of how would this affect your understanding of this? I think this question is very important because we need to value what we have and convince that the people that we still need to keep the things that we're having instead of throwing promises to people. So
Yeah.
I want to ask you this question.
Yeah, thanks. So this question is important also for people who give us money. So in that respect, the answer for me is quite straightforward. If you ask me for the videos of site register, which is, I think for me that's really the next big thing. And for us, we are already at the very limits of what we can do with this. If there was anything less, we have already had attempts done in the with less data to do what we are doing, and it was difficult. This is the bare minimum that is required to do something with it. So this is already the bare minimum for videos. Now for the images, especially the ones that you see on the screen, we also did this thing called jackknife test, where we remove a particular telescope and then look at how the images look like. So we have 9 stations for this particular data. And as you can see, the Greenland telescope was useful in many respects in reducing our uncertainties on everything. But there is one telescope that if we don't have, basically nothing works. That is ALMA. ALMA gives us the most amount of sensitivity. If we did not have that, we couldn't do this. So I would say that the first time EST did its observation with 8 telescopes, that was already the bare minimum we needed to do things. Now we are adding more telescopes to do things, but not to answer the same questions, but to answer more complex questions. And that's why also that's also the bare minimum needed. Always when we add new sites, we test whether that what value that site particularly adds, and only when that study is done, we propose to add that particular site. So yeah, that's pro. I think in general, what we are doing is already on the limit. Would be my answer.
Okay, thanks a lot. And so now we're going to the second part of the thesis, which in which case I will ask everyone to leave the room where we can debate the committee.
The lights are from the remote. I think it's number 1. Oh.
Okay, welcome back. So, Ron, thank you for coming back. I think, we sat down, we discussed it. Clearly, you've done fantastic work, and the presentation was very, very good. This was unanimous by the committee, and so it's my pleasure to say that we decided to award you the doctor with sobresaliente, and congratulations.